let's talk about, we're back, just in case you're wondering. Let's talk about rigid body rotation, about a moving axis, which is a fancy way of saying we're going to do more acceleration constraints, okay? So before, when we dealt with pulleys, we pretended that pulleys were massless points, which is not a really good approximation for a pulley because, you know, they don't actually work like that. So here we have a pulley with a non-slipping rope. Why do you think non-slipping is important? Well, friction is what makes it not slip, yeah. So that, well, because it's an acceleration constraint, right? So if this thing's turning at this speed, the rope is also moving at the same speed. If it slips, then they're kind of out of sync and you have to calculate them separately. So we're going to assume that you don't have slipping because that makes it easier and it gives you an acceleration constraint, okay? Which means that the angular acceleration of this should match the acceleration of this going down, which is kind of a neat thing. So in this case, we know that the velocity and acceleration should match with the angular velocity and acceleration connected by the radius of your pulley, okay? Now the signs are a little bit tricky, just like before. So remember this, you always want to point, pick your coordinates so that, well, my trick is to pick your coordinates so that acceleration is positive, and match all your forces and torques to the positive direction and make sure you're always going in the direction of acceleration. So that might mean in this case, right, this is clockwise. So you would call, and like I said, default is counterclockwise is positive, but you can choose your coordinate systems just like before to be opposite if you want them to. So you can choose this to be positive angular acceleration. You'd also choose down to be positive, or you can make them both negative. That works too. Okay, but you just have to make sure whatever the sign of this acceleration is, it should match the sign of this acceleration. So when you do your system of equations, you don't mess up. Okay. All right. So this is and basically the tangential the tangential velocity at the rim should match this velocity. The tangential acceleration at the rim should match this acceleration. Okay, because everything is moving together. So this is just an acceleration constraint problem, but now including torque. All right, cool. Let's try a clicker question. We're thinking it's one of these. Please discuss. We'll vote again. Think about this as torque, moment of inertia, acceleration. Oh no, the starburst at the wrong time. Oh, this is unfortunate. Okay. What do we know about the torques? The same, right? mg, right? That's your force. What's your distance? Same. The radius, right? So the torque should be the same. What do we know about the moments of inertia? Right, they're different. So which one has a bigger moment of inertia? This one should have the bigger moment of inertia. Okay, so same torque, larger moment of inertia. What's going on with the acceleration? Less acceleration. That means it speeds up slowly. Okay, this one, smaller moment of inertia, which means bigger acceleration. No, I turned it off. Bigger acceleration, which means faster, right? So it's going to drop to the ground faster because it accelerates faster. Because remember, it's easier to spin in this configuration than in this configuration. Okay, so this is this configuration one, and so it's going to spin faster and drop slower. So bigger moment of inertia means it's harder to turn it. Okay, so the answer is going to be the block attached to the solid cylinder, which is A. This is like the worst outcome we've ever gotten from a clicker question. So sometimes we just get random answers, but you guys were really sure about the wrong answer. So that's fun. Okay. It's like clear that out. But do we understand now why it's A?
Yeah.
Okay, so moment of inertia, larger moment of inertia means it's harder to turn things. Okay, cool. We're going to do this problem, which is going to take forever. So I'm going to get started. Please read it while I try to switch over to this other thing. All right, so let's do a rope and pulley problem. I hope I get to this one. I found it. It got moved. I had to like search all over the place for it. All right, so we have a 2 kilogram bucket. It's attached to a massless string, very, very normal thing, massless string, that is wrapped around the 1 kilogram, 4 centimeter in diameter cylinder, which rotates on an axle through the center. The bucket is released from rest 1 meter above the floor. We want to know how long is it going to take to reach the floor. So basically, this is the problem of the clicker question with the solid cylinder. So we are going to start by doing what? Yeah, let's draw a picture. And since I'm not good at drawing cylinders, I'm going to draw a circle. Can you guys, yeah, you can like imagine what that is. Okay, so here's our cylinder. No. It's funny, if I try to draw the circle better, it makes it worse. Okay. And, okay, nope. Okay, now I've done this, it's gone too far. Okay, so we have the radius of our cylinder. We'll call that R. And then there's a bucket hanging off of it. So we'll go, do we want to make it turn clockwise or counterclockwise? Which one brings you more joy? You want clockwise? Okay. You're really sure about that? Okay, so I made the string small because it's massless. And bucket released from rest. Okay. Here's a bucket, and then it's 1 meter above the floor. Okay. And we're looking for time. So that's delta T. The bucket is 2 kilograms. We know the radius. So radius is going to be 0.02 meters. We know that the mass of the pulley is 1 kilogram. So that we'll call that big M. Mass of the bucket. Mass of the bucket is 2 kilograms. Sorry, the M's are not matched to the sizes, but you get the idea. And then where do you think we should start? This is a dynamics problem. Let's start by drawing some forces. So where are the forces? Bucket. What are the bucket forces? There's mg and tension. Okay. What about the pulley forces? Torque isn't force. Think simpler. Tension, yay. Okay, tension, which we'll use to get torque. So you're just ahead of us. Okay, and then what are the accelerations? We have an angular and linear acceleration. So there's an acceleration here that's we'll call alpha. And then there's an acceleration here we'll call A. And we know that they are coordinated, right? So that means there's some way that you can put them together, which is A is equal to alpha times R, okay? And I'm just gonna put that there just so you know that we need that later. All right, let's start by calculating some torques and forces, okay? So let's say, what's the net torque on your cylinder? Like, what is the torque on the cylinder? It's only one force, right? How do you calculate the torque? Tension. So torque is going to be T times R. Now, let's pick our coordinate system carefully. So let's say that this direction is positive. Let me do it in gray, actually. So I know we just said that counterclockwise is positive, but because we pick clockwise, let's pick clockwise to be positive, and we'll pick down to be positive, okay? Just because that makes everything easier. But that means any force that points down and any torque that goes clockwise is positive, anything the opposite is negative, all right? That will make our lives slightly simpler when we start doing the algebra. So here's our torque. It's TR. We also know that torque is equal to I times alpha. So torque is equal to I alpha. We're going to need to calculate I, right? I is 1/2 mr squared. Do we want to calculate this with numbers, or do we want to do it symbolically first? This is more of a personal preference thing. Symbolically? Okay. So the first thing we're going to want to calculate is tension. So let's figure out what tension is. So we can do that over here. Remember, if we sum up all the forces in the y direction, that's going to be, oops, remember, positive is down. So that's mg minus tension is equal to ma. Okay. You feeling okay about that?
Yeah.
Okay. So now we have an equation for tension here. Then over here, we have torque is equal to, so we're going to plug in torque. So that's going to be TR is equal to 1/2 mr squared times alpha. Okay. Everybody understand what we're doing there? Okay. And then, so here's our three equations. Here's our torque equation. Here's a force equation. And here's our angular acceleration equation. Okay. What are we going to do with these? What do we need to find? So what are we trying to? We need acceleration, right? Why do we need acceleration? To find the time, okay? Because we know the position, we know the change in position, right? We know if we know the acceleration, we can find the time, okay? So we have three equations. How many unknowns do we have? 3. So can we solve? And do we want angular acceleration or regular acceleration? Regular acceleration. So we're going to solve for regular acceleration, which is this. Okay. So to do that, we're going to take our three equations. I'm going to move them over. I'll move this one over here. So here's our three equations. And we have 3 unknowns. I'm going to move this over here to get it out of the, move it down there. Okay. So 3 equations, 3 unknowns. Let's do some algebra. So we can take, see, fun times. Let's solve this one. Okay. I know what we're going to do. There's lots of ways to go about this, but we're going to first solve this for alpha because we want to get rid of alpha because we want A. So this alpha is going to be A over R. Okay. And then we're going to plug that into here. So this becomes TR is equal, oh, we can get rid of one of the R's. Cool. So tension is equal to 1/2 mr. Oh, we're going to get rid of the other R, alpha, which is A over R. Okay. Cancel the R's, very satisfying. And then we end up with T is equal to 1/2 m alpha. Okay. Then we're going to plug that T into it should be A. Yes, it's A. Good catch. Let me make sure this looks like A. It's also very important to have good handwriting when you're doing these problems. Okay. All right. So we're going to bring this guy over here. Sorry for all the arrows. This becomes mg minus 1/2 ma is equal to little m a. I think that looks good. All right. And then we're going to solve for a. So that becomes mg is equal to m plus 1/2 big M A. So A is going to be M plus 1/2 large M divided by mg. We plug all our things in. So that's going to be, oh gosh, I chose these badly, but 1/2 the bucket. So this is going to be 2 kilograms plus 1/2 times 1 kilogram, 2 times 9.8 meters per second squared. I'm all out of space, but the acceleration is 7.84 meters per second squared. Okay. All right. Done with systems of equations. Now what do we do with this information? We find time. So what equation might we want to use for that? Well, we have distance. We have acceleration. So I'm going to choose this one. Okay. Oh, A, sorry, not G. It's not free fall. Okay. And this is our A. We also know that we have delta Y over here, and that goes here. What do we know about the initial velocity? Conveniently 0, so we don't have to do a quadratic equation, which is very, very nice. So we just solve for t. Oh, and this should be positive. That's positive. Oh no, they're both negative. Okay, so you end up with, this is negative, but remember, what's final y? It's 0 minus 1. So there's a negative on both sides. The negatives should cancel. This should be negative 1. So don't worry about the negative. It works itself out. We end up with t is equal to 2 delta y over a square root. That's going to be 2 times 1 meter divided by 7.84 meters per second squared. And that's going to give us a time of 0.505 seconds, which is our final answer. Okay. Any questions on this? I know it's a lot. We've now basically come full circle and we're using all of the physics we've ever learned in like one problem. We didn't use any energy. So there's that. You can actually, you can solve this problem with energy too. Okay, so to review, start by drawing the picture, draw the forces on the picture, figure out what you need to know. If we need kinematic stuff, solve for acceleration by using acceleration constraints and your force and torque equations. Yeah? Okay, so a lot like what we were doing with just dynamics, but now with extra steps. Cool. All right. Don't have any questions? I'm moving on. Let's talk about rolling. Okay, so we've talked a little bit about how wheels work with static friction. Remember rolling, we talked about how there's, if you have something sliding, that's translational motion. If you have something spinning, that's rotational motion. If you have something rolling, that's both. Okay, the most special case of rolling, meaning the one that's easiest to solve, so we like it the best, is rolling without slipping. And the reason you want rolling without slipping is because when you have rolling without slipping, you can assume that the angular speed of this thing is equal to the tangential speed at the top, which should, sorry, at the middle. Okay, so equal to the speed at the middle. So essentially, Translation says this whole wheel is moving like this. Rotation says that the top is moving this way while the bottom moves the other way. And if you have rolling without slipping, the center of the wheel, right, the whole object moves the center of mass that's equal to the angular velocity, okay? So the center of mass velocity is equal to the angular velocity times the radius of the wheel. All right, that's the rolling without slipping constraint. It looks like this. So the velocity at your center of mass, so like basically the speed your car or vehicle would be moving if it was carried by this wheel, is going to be equal to the radius of the wheel times the angular rotation, angular speed of the wheel, okay? The other thing to remember is in the case of rolling without slipping, both this is true and you have to use both kinds of kinetic energy, okay? And the nice thing about this is you can see, if you plug this in over here, now you have a new kinetic energy for rolling without slipping. You can write all in terms of either velocity or angular velocity. So you can use this to convert back and forth. Okay. So remember, if you're rolling, you use both kinds of kinetic energy. If you're rolling without slipping, you get to use this extra thing that makes them connected. Okay. Okay. So we're not going to start this. Well, yeah, we'll do this question and then I'll show it to you. So let's start here. I think it's A, B, or D. There's A, B, and C in the chat. So please discuss. We'll vote again. A or D? Okay. The answer is going to be D. But we'll go through the math too. But before we do this, we can do a little test. I don't have a particle or a sphere, but I do have two things of the same radius. So here, it actually doesn't matter that they're the same mass, but I think they are. So here's the this is gonna like break my computer. Well, because that way then it's already chipped because of that. I've made all of these mistakes before. So we have a cylinder that's hollow and a cylinder that's solid. Okay, which one has a larger moment of inertia? The shell, yeah. So which one do we expect to win? Wait, what is this one asking? Last. Which one will reach the ramp last? At the end of the ramp last? The hoop, right? Because the one that's solid should spin faster and accelerate faster, correct? Okay, let's try it out. Oh my gosh. Yeah, I can take things down. But yes, so just in case you didn't believe me and the math is it in action, okay? How would you actually do this problem though? Yeah, they're all the same, right? They all start with mgh. So potential energy is just mgh. But we have different kinetic energies. So remember, the kinetic energy for all of them is 1/2 I omega squared plus 1/2 mv squared, okay, for the center of mass. But remember, the moment of inertias are going to be different. The other thing, it's rolling without slipping. So we also know that V is equal to R or omega. We can deal with that later. Okay, for the, let's start with the particle. So kinetic energy for the particle, that's going to be 1/2. What's the moment of inertia for a particle? It's just mr squared, right? Because you don't have to integrate anything. So it's just mr squared, omega squared, plus 1/2 mv squared. Oops, made the wrong m. It got so complicated we forgot what the moment of inertia for a dot is. So that's pretty normal. So if we sum all this up, remember r omega is equal to v, right? So we could just say this is v squared. So this becomes 1/2 mv squared plus 1/2 mv squared, which is what? Just mv squared. Okay, so this is the kinetic energy of a particle. All right, how about for, let me move this out of the way. Let's go to the sphere. So that's 1/2. What's the moment of inertia of a sphere? I think it was 2/5. Solid sphere. 2/5 mr squared. Okay, so this is 2/5 mr squared omega squared plus 1/2 mv squared. Okay, this gives us 1/5 mv squared, because remember this gives us v squared, plus 1/2 mv squared. So what's 1/5 plus 1/2? 7/10. Okay, so this is 7/10 mv squared. All right. Okay, so that's for the sphere. So I'm going to make that smaller and move it over here. So we've got 1, and now we have 7/10. Let's try the cylinders. So kinetic energy, that's 1/2. Solid cylinder is 1/2, and empty cylinder is the same as a particle. Okay, so, oh, duh. The particle one, does it matter what the moment of inertia is? I messed that up. For the particle, doesn't matter what the moment of inertia is. What's the kinetic energy for a particle? Well, can a particle rotate? It's a dot. No. So K for the particle is just 1/2 mv squared. We did math for nothing. I'm sorry. So for the cylinder, that's going to be, what was it? 1/2 solid cylinder. Yeah, 1/2. Yeah, it was going to end up being the same as the particle, which was going to make me look dumb. All right, mr squared omega squared plus 1/2 mv squared. So this gives us mv squared plus 1/2. Oh no, that's 1/4. 1/2. Sorry, I've forgotten how to do algebra and just arithmetic. So 1/2 times 1/2, guys. 1/4. 1. Okay, so this gives us 3/4 mv squared. Okay, so here's the sphere is 7/10. This is 3/4, and then last but not least, the hoop. That's going to give us, hoop is mr squared. Yes. Yeah. So 1/2 mr squared omega squared plus 1/2 mv squared. So that's going to give us 1/2 mv squared plus 1/2 mv squared. So that's just mv squared. Okay. So this one, oops, has the largest one. Okay. That followed by 7/10, followed by 3/4, followed by 1/2. Do we follow? Are we? Yes. Does the mass matter? So if they all, if these things were not the same mass, would you get a different answer? Are you sure? Well, because if we look at this, right, you have mgh is equal to, let's just pick any of these, like 7/10 mv squared. Mass cancels. So it actually doesn't matter if these things are the same mass, only the shape matters. And it does matter that they are the same radius. Okay. Cool. Any questions?